Okay, let's review the simplest case that we can look at with spectral modeling. So I think I call this number 2. And we're going to have a simple equation, du dt plus c du dx is equal to 0. And we're going to try to solve this via the spectral approach. Little c in this is a constant. And so the spectral approach is that we assume a solution u of x of t as a sum of pieces, each of which is well known in its character and behavior. So let me finish writing this, and then e to the I m k x, and we'll call this b. All right, so the d's are called variously weights or expansion coefficients, and those become the unknowns of the problem. And I'm using uppercase curly D for this. The weights carry the time-dependent part of the problem. And then over here, we have some well-known stuff, e to the I mkx. Well-known as in, we know what's going on mathematically. And then we'll do the sum initially from minus infinity to plus infinity, but of course we won't be able to get away with that for very long. Okay, so the beauty of the spectral method is that we can calculate the derivative exactly, not approximately, which is what we do through finite differences. So if we substitute the expansion b into our particular equation A, then on the left-hand side, the du dt term becomes the sum over little m of the time derivatives of the expansion coefficients with respect to time, e to the I k m x. And then on the right-hand side, this is equal to negative c times the expansion, again over m, of the derivative. So d is still in there, and the derivative of e to the I k m x with respect to x is I k m times e to the I k m x. All right, now, as I mentioned, these pieces are known, the e to the I k m x pieces are known, but what is not known is the expansion coefficient. So what we're going to do is ultimately solve for the d's in this problem. Okay? And you cannot go through cancelling here. I know it's tempting to do that based on every math thing you've ever done, but you can't cancel the e to the I k m x and the sigmas and all that kind of stuff. You have to be slightly more careful. So instead, what you have to do is use the orthogonality properties. And once we've done that, we'll have an expression for the expansion coefficients. And so how that works is as follows. You multiply the expression on the previous page by one of the functions. And actually what you have to do is multiply by the, I think, the complex conjugate. Certainly when you're talking about sines and cosines. So you multiply by e to the minus I n k x, where n is the same as one of the little m's. And then you integrate. And then you use the orthogonality condition, which is that the integral of e to the I m k x multiplied by e to the I negative n, whoops, hang on, get rid of that, e to the I n k x integrated dx from, let's say, 0 to capital L across the domain. This is equal to one of two things. It's equal to 0 whenever n is not equal to m, and then it's equal to something when it is. And I didn't look up what the something is. You know, there could be a 2 pi L in there. It depends if you've normalized the functions or not. If this was sines and cosines, then this quantity would be the area under the curve, and it would be something with 2 pi L, K, all that kind of stuff. But the point is that it's non-zero. So what we get out of this, once we use the orthogonality, is we get on the left-hand side d of, oh, my software's getting a bit jumpy again, d of this dt. And actually that's not m, we really should write that as little n because that's what we chose earlier. And this is equal to minus I k c d of n. So our first order partial differential equation that we began with becomes just an ODE for the expansion coefficients, one for each of them. And what we would now do is solve this using, I think I began to see what's going on with my software here. But anyway, we solve this via finite difference methods. You know, you go off and you look at your time integration schemes that we looked at earlier in the semester. You find the very best one, and so on and so forth, and you use it. So the new value of d feed back to give you your new value of u, and hence the problem is solved using finite differences.